Okay, so when the resources are ready, srun will be executed. So this is a list of the commands of Slurm. So the first two are actually the first three. This is not entirely true. srun is not submitting, but sbatch and salloc. So the first one submits a job script. salloc just request resources. sq list the jobs that are in the queue, and you may pass an option like -u, your username, to only see your jobs in the queue. And scancel with the job ID, and the job ID is something that you get with sq, allows you to stop or actually kill a job that may just be in the queue or may already be running. So this is very useful while you see that something is going wrong and your job for some reason is not responding, so you can just kill it and leave the compute resources for someone else. Honestly, I think that this is all you need for today. So sbatch, sq, scancel is all you need for today, for controlling the jobs of today. And we will only, so I think this is it, because we will only execute serial jobs on the CPU. So we will not have MPI. So srun is enough, and what you only have to put there is the job script that we wrote this morning. So just write down these three commands: sbatch, sq, and scancel, and sq -u and your username will list the jobs currently running. Be careful, because as far as I understood, you are sharing the usernames, so you may see jobs that are not yours, but since you are sharing the username, this is something that is, well, shouldn't be done and it's uncommon. So you also have the right to kill others. Yes, your neighbor jobs. So don't do that. Be a good person, and that's it, I think. For what concerns Slurm, if you have questions, you may just interact with point-to-point interactions that you now know very well. I want to spend a few words on the hands-on that is probably the most important one in this afternoon session. Okay, so your task in this hands-on session is to create a CUDA version of the CPU program that does this Monte Carlo sampling to get the area of the circles. So I'm already telling you that there are two functions that you should focus on. These are uniform and is inside circles. I don't want to go into the details, but so the naming convention should be that you create a main.cu file that will be compiled by the CUDA compiler, which is NVCC, and that you see here. If you don't like to write C, or you just prefer to go directly to the solutions and check them without trying, don't forget to add all the files that are in the solution folder. There is also a kernels.cu there. So of course you have to compile both. So just add it here. If you are interested instead in trying to write your own version of this code, well, uniform should be fairly simple to parallelize. This is a bit harder, but you just need the concept that we introduced this morning. And I am providing here, yes, in the README file of the repository, a few a portion of code that you can just copy paste in your CUDA version of this method, of this application, to obtain the random numbers directly on the GPU. So these are just helper functions to make it easier to debug the code. So this will tell you where an error happened, if an error happened, and this is needed to call current functions. And below here you can just copy paste this. This is more or less GPU current initialize and current finalize. So you just copy paste this at the beginning, and you can use this function here to collect, to try random x, to try numbers inside random x, where random x is a variable possibly on the GPU. No, well, possibly is a variable on the GPU. Okay, so there must already be some space in the global memory, so allocated with CUDA memlock, where random x point to, and that can host to try many double numbers, double precision numbers, and eventually to clean up with CUDA destroy generator. Okay, so I think this is it. So the task is mainly allocate a buffer for generating the random numbers on the GPU, generate them with this code. As I said, this part should be at the beginning. This is what you need to collect more random number, and this must be at the end. And then write the CUDA kernels for uniform and for is inside circles. Questions?
About if they have random functions.
Yes.
Inside you can put any C code.
Right. So thank you. Very good question. So yes, for what concerns this particular problem, yes, you can use circles. You just have to copy the memory that is allocated on the CPU named circles. I can probably show it, but yes, I mean I can show very quickly. Voila, you can use circles, so you can just put the circles type here, circle type, and of course you can copy it with the size of circle. So hope this answers your question. Yeah, and all the other types are
So any kind of class object how you can put it.
sorry, say it again.
Any kind of object.
Structures can be created, yes, you can access these structures.
I'm thinking C++ behavior. Does it still work in
Yes, I think it should work. Yes, yes. I'm sorry. So honestly, I mostly do Fortran programming, where you only deal with types and stuff like that. But so I'm not. Yeah, I think the structures, as long as you copy all the structure, is fine. I have to check on the documentation for limitations in the types that can enter CUDA kernel.
So the plain old data.
Sorry?
The so-called plain old data in the C++.
Yeah.
This plain old data can be.
Yeah, certainly.
May I ask a question about calling the kernel?
Yes.
So we have this strange
Syntax.
with the less with the number of a batch and the number of threads.
Yes.
Those are dynamical numbers or must be statically?
No, you can put variables there.
Could you repeat the question for the
Yes. Oh, yes. So the question is, I can also show the presentation maybe, so it's easier to follow. The question is, can you put variables here? I think that also anyone shows. So you can put a variable here.
Okay.
Okay.
It is static. Can be changed in runtime.
Can be changed.
Yeah, but once it is called, it won't change anymore. I mean, in the
During the execution of the kernel, no, of course, no, sure. So when the kernel is executing, no, these number remain fixed. You know, the block dimension and the thread and the number of threads, the thread dimension, they remain fixed. Yes. But of course, you can use the same kernel for different sizes. Yes. Sorry, there is an important information that is probably missing, and uh, and it's useful to simplify the development. You can pass scalars to CUDA kernel. So, like the simplest function to port is probably uniform.gpu, right? And this is from the solutions. It's valid. So random x is a pointer to global memory on the GPU, and you can also pass the minimum and the maximum as parameters to the CUDA kernel and use them inside the CUDA kernel. So the CUDA runtime will take care of moving this data and have it available on the GPU. Of course, you cannot do the same, so you cannot set pointers. So addresses, as I told you today, are not available. You cannot access memory addresses of the RAM from the GPU. But it's fine to pass a value to the CUDA kernel here. So you can avoid allocating a global memory for these two variables that you have computed at the beginning, Okay? Now this simplifies a bit the development. By the way, how many of you already managed to do this function here, which is more or less like the add function? All of you managed to do that? No. Okay, well, some of you. on. Sorry, another announcement. I uploaded the complete code for doing the dot product in the directory slides. In the repository with the exercises. So you do find it here. Slides. Whoa, where is it gone? No. Slides here. You do see a file which is CUDA dot. That's the code that performs the full code that performs the dot product that we saw this morning. Maybe it's useful for copy pasting stuff. And another important comment, there was a let's call it a typo in the README of this exercise. So I wrote that random X can be a device array. It must be a device array. Otherwise, bad times. You have bad times. Another useful comment, maybe. NVCC, when you compile a CU file, which is the extension for a CUDA source file, actually NVCC is a C++ compiler, so you may find that min and max, if you copy paste the C code, are already defined. That's because it's a C++ compiler. You can just remove min and max or rename them to min something and max something, and the error goes away. Okay, so I saw many of you getting pretty close to the solution. I think we could just stop for a while, introduce the last concept of OpenACC, and then maybe you can go back later, and we have some more time for more hands-on. You may decide to switch to OpenACC or finish this task if you want. So maybe I discuss the solution at the very end of this afternoon, and so that I don't spoil the solution if you want to continue working on this. I'm just showing the difference. I recompiled the code with ECC, Intel compiler. So with some optimization, I managed to have it running in more or less in less than a minute. Now I run the solution. So no, this is not the right. Voilà. So now I run. So I will run it on the login node. It's not the best thing, but I mean I did it also for the CPU version. So this is the GPU version. So we squeezed the execution time from a minute to 3 seconds and a half. And it's probably not even the best result that you can obtain. You can still optimize much more. Okay, so let's be honest, this is not a fair comparison. I'm comparing a single core against a GPU. So to make a fair comparison, I should implement the CPU code with OpenMP. And you're welcome to do so if you want. And then finish this comparison and check the speed up that you obtain with the GPUs. So, okay, I discuss the solution, or I present the solution later. Let's now move. Oh, okay, fantastic. Let's move quickly to a different approach to general purpose GPU programming, which is OpenACC. OpenACC is more or less the approach taken by OpenMP, but for accelerators. Actually, the idea was that OpenACC should drive the description, the definition of the OpenMP directives for accelerators. And that's what actually was done. And we have also a set of directives to exploit GPUs within OpenMP. Not sure if you have seen them in the first 2 days. Well, they're pretty new, so maybe, I don't know if Fabio introduced them, but anyway, OpenACC is specific for accelerators. So, at least it's designed for accelerators. What you do is similar to what we have seen for OpenMP. So you use compiler directives, and it looks like this for C, and looks like this for Fortran. Nothing very new. And how can you compile and make use of these directives? Well, you have a set of compilers. The new version of GNU 8 something, is able to compile, I think it's the standard 2.0 of OpenACC, and has nice performance. So seems like we are getting closer to having an open compiler that can produce binaries and understands the directives of OpenACC. Then you have PGI. PGI is not open, it's a commercial product, but there is sorry. It's a commercial product, but you have a free community edition with I think the license lasts 1 year and a half. 1 year and a half probably. But they make a new release every 6 months, I believe. So at the moment you can have PGI compilers for free, and you can compile OpenACC code with this. And these are more or less the compilers providing the best performance. And then you have other private compilers, so commercial compilers, Cray compilers. You only have them on supercomputers sold by the Cray company. So no, probably in order to use them you have to access a computer provided by Cray. And there is also this fantastic Chinese compiler. I don't know actually how to read this, but there is also this compiler that apparently is able to understands OpenACC, and quite a lot of work has been done and has been presented recently from the Chinese supercomputing centers for working with OpenACC. So today we will focus on PGI. With PGI we can compile both C, C++, and Fortran codes. So and the syntax is simple enough. You need to add this line here, which stands for target architecture. Tesla is the architecture of our GPU. CC35 is the compute capabilities. CUDA 8 is the toolkit. And you also have a simplified version. You have a simplified option to link CUDA libraries. So you just have to specify m CUDA lib current, and all the linking option will be already in place. And this is how it looks like. But one very important thing is that since this is a directive-based approach, is the compiler generating code for you, and you can have extremely important information on what the compiler is doing by adding this option here, m-m info equal acceleration, ACCEL. So this is what you should actually use in the rest of this afternoon. So let's start, and once again I will focus on the two tasks that we show saw this morning. One is the add function, how it becomes with the OpenACC. Well, this is the version written in C. First thing we have to do is, as I told you, move data on the GPU. How we do that? Whoop. We have a directive to do so, and it looks like this. Pragma H, and this specifies that this directive is an OpenACC directive. Data is a type of directive that we are introducing now, and then we have a list of information that we want to provide. And these are create and copy out. Guess what they do actually? Create will create a portion of memory long from 0 to n on the device, and copy out will copy the data from C on the device to our host. Let's understand this a little bit better. What does create do? Create tells to the compiler that it should allocate an array and call it A and make it n elements long and do nothing but that. Copy out tells to the compiler that it should create an array which is so-called C and is element as n elements start from 0 and starting from 0, and when the scope of this directive ends, the data in C should be copied. Where does the scope ends? Here, you see the brackets. Okay, so here there will be a copy. Where will it be copied? In C. Okay, so how does this work? There is a mapping between the variables allocated on the host and the variables that gets allocated on the device as a consequence of this directive. So depending on what you see after the data directive, a number of behaviors is possible. I will go through all the possible behavior in a second. Let me introduce another directive and let me stress again one thing, because this is very nice. You see all the CUDA malloc, these long allocations, long API calls are gone. Looks fantastic, but the price to pay is that you're kind of, you have to be very careful when and understand very well where the data and when the data are present on the device. So what happens here, that an allocation will take place here and will last until the scope of this directive ends. So the allocation takes place here and no data, so a deallocation will take place here. And as a consequence, you will spend time allocating and deallocating data before add and after add. If this is clear, I can introduce another option, which is this is the definition that I was just telling you. So this is just to this is what I just told you, and this is just to introduce also the syntax for Fortran, where you have to explicitly specify the end of the data construct, like with end data. So what if you want to keep the data on the device for a longer time? Suppose you have some initialization data, like the dimensions, or in our case the circles, right? And you want to keep them much longer than the scope of this data region, which is inside a function. You want to have it, for example, in C++, could be the initialization of the class, and maybe you want to remove them when you finalize, when you destroy, and you have the destructure. So for this, we have unstructured data regions. So what I've shown before, what I've just showed is structured data regions, and then we have unstructured data region. How do they differ from the previous one? Well, you specify pragma h enter data, and then you use the same syntax that you saw before. I will go back to that in a second. And this allocation will last through all the code execution until the corresponding exec data is found. So how do you specify what you want to put on the device with both data and enter data? Well, copy in I think it's pretty easy to understand. I will go through all of them, but should be trivial. Copy in means allocate and copy when you enter the data region. Okay? And this can be used in both enter data and data. This means that this will not be copied out when you leave the data region, right? Copy out is more or less the opposite. Allocate, don't copy anything, but move the results back on the CPU when you exit the data region. Copy is the same as above. So it's the two above combined. So you copy in when you enter the data region, you copy out. Create. Well, create is just the same thing, but don't copy anytime. You just create some space that you need for your computation on the CPU, and then remove it when you're done. Never copy data back and forth. This is, of course, something useful when you exit data. So it's only for unstructured data. You enter data, and you specify, for example, create some space or copy in some variable. When you exit data, the deallocation, what could be free in the C syntax, is delete. And this will remove the data from the CPU. Present in a data region has an very important meaning. It means that within the scope of the data region, when you will use a variable, the equivalent version on the GPU is already present on the device. Maybe this is a bit confusing, but we'll see an example in a few seconds. Okay, so we have seen how to copy the data, right? So someone noticed, I don't remember who, but someone correctly told me, and this is true also for the example that I showed earlier with CUDA. Why are you copying this A and B since you didn't actually set any value? This is an example, and it's meant to just show the syntax and be as concise as possible to fit into the slide. Of course, if you want to add something, I suppose that you filled it somewhere. So in here, in between this C and this directive, I assume that you filled A and B, and therefore you want to copy them before calling the carrier. So you copy in A, B, you want to copy out C. You don't care about A and B because you are only using the sum. And so let's make add an accelerated function. Okay, so we have a data region here, which lasts from here to here. And this is where present comes in. So here we are telling the compiler A, B, and C are already present on the GPU. And then, well, getting the acceleration in OpenACC seems like magic. You just throw in a pragma h kernels. What is pragma h kernels? Well, yeah, oops, sorry. I think I'll move to this later. In any case, this is a directive that tells the compiler, please accelerate this part. I will go back to this in a second. Let me finish the data synchronization and data management with one other directive that we forgot, and is update. Okay, So with well, I think it's pretty evident what it does, right? So it updates the version on the host or on the device of a variable. So you see that the idea is that we have a mapping defined by the name of the variables, and we use these names to update the data on the CPU and on the GPU when needed. It's okay for everybody, this part of data management? Okay. So let's move on. Okay, that's where I wanted to introduce kernels. So what is kernels? Well, it's an indication to the compiler. We are telling the compiler that we believe that a region of our code, and maybe a long region, can be made parallel. It has trivial parallelism, so we believe that the compiler can easily turn that part of code into a GPU accelerated function. I mean, look at this add function. Everything is independent. Writing the CUDA function was pretty easy, so come on, PGI. We pay, well, we as Cineca pay. You don't pay any longer, but we paid for the compiler, so try. And that's indeed what the code will do. It will try to identify parallelism. It will identify which data must be transferred, for example, scalar variables. It will create a kernel, and when the function is called, it will be offloaded to the GPU. And eventually it will also add an implicit variable at the end of each kernel that is produced. So this seems fantastic. Okay, so you know, how do you parallelize code? Just throw in H kernels. Great, right? Okay, so it's not that nice. You remember this super simple loop here? I mean, okay? And you remember that I told you always use info accel? And here's what the compiler tells you. Okay, so I tried to parallelize that code, but the loop carries a dependence. B and A prevents parallelization. Dependence of C pointer prevents parallelization. Backward dependence of C pointer prevents parallelization. So eventually he made a sequential code. What does this mean? We haven't seen this. We'll see this in a few slides. What does this mean? It means that this add will be executed by a single CUDA core. So it will be extremely slow. It will slow down the whole your application. And why did this happen? Probably those familiar with C know the answer. No one. Okay, the problem is that we don't have any guarantee that the pointer do not overlap. So the compiler wants to be safe and says, so if you are aliasing one of these pointers with another variable in this input, you may be doing something that cannot be parallelized. So there might be a dependence between this addition. And so I want to be on the safe side and make it sequential. And this is extremely bad for you. You have two options. One is to use the restrict keyword. I don't know if you know it, but I mean, it's pretty technical. So you have another option, which is the one you see here. We'll deepen what H loop is in a second, but you can tell the compiler that the following loop does not carry any dependence. And now it's your fault. You said that if there are actual dependencies, this will generate garbage, and it's up to you. But I mean, we know what we are doing, we know how to sum numbers, so you know that this is fine. And if we look at info acceleration, now it looks pretty much better. It tells us that is replacing our kernel with this syntax, which looks pretty strange, but well, we'll see what pragma hatch loop is in a second. And what we do see is that we are having vector, and we have a number here that actually is very similar to the one that we saw before when we were discussing threads. And indeed, the gang and vector, as you see here in the comment, resemble block edx and thread edx. So this is something that is good for us. Hatch loop, we'll see in a second what it means, and this that accelerated kernel has been generated. And at the same time also the data copies. Okay. So what if we don't want to be in the hands of the compiler, but we want to actually have a parallel region that is executed on the GPU? This is the directive hatch parallel, and with this directive we guarantee that it's safe to make a parallel region. There are no dependencies between the array elements that between the mainly loop elements that will follow. So what will a compiler do in this case? Well, there must be a directive next to this. So this will open a region that is executed on the GPU, and what is actually going on the GPU will be defined by the directive that follows this one. We'll see it in a second. The compiler will again identify which data must be transferred, scalars for example. We'll create a kernel with local variables inside the parallel region created as we did in the CUDA version. We'll execute this kernel on the GPU, and we'll create a barrier, an implicit barrier, at the end of the parallel region. So this is slightly different from the thing we saw before, right? So I told you earlier this morning that when you call a CUDA kernel, it returns immediately. Here instead, there is a barrier at the end of the parallel region. Okay, so here's the loop. I think that is more or less the only directive that we see for today. And what it does, well, it tells that it is safe to parallelize the loop that follows this directive. It tells that there is a loop following this directive, and that you should parallelize it, and specifies information of the following loop. So it describes the type of parallelism and defines the variables, the arrays, and the reduction operator that should be done on the loop that follow. A few important things to know. There are a number of variables that are private by default. I think there are more than this, but to keep it simple, you can consider that variables of the loops in C and Fortran are private, so you don't have to make each variable of the loops private. Variable declared inside the parallel region will be private, and variable declared in procedure carried from a compute construction. This means that if you have a variable declared in another procedure called within a compute construct, so like the parallel one that we have, will be private. This is I should probably not mention this because it's more advanced. We will not see something like this, but you have it here. And loop independent, you have already seen it, so you can combine these two. What do they say? Well, we are telling the compiler that the next loop should be parallelized and has no dependencies. So one example where this is important, not only the case that I showed before, is here. You see, the compiler may not know that m is always greater than n in our loop, because that depends on our input to the function that we're calling here, to the code that we're calling here. So this tells the compiler that it's safe to parallelize this loop, and that's the same as we saw before. Remember that this was needed in ACC kernels, but if you have a parallel region, so instead it's Prague ACC parallel, this independent is implied. I told you so earlier, right? And I think we move to one of the last slides. So what if instead we have a loop that we need to run sequentially, no matter what? You can specify that as well, and it's the case that I'm showing here. So to recap, we have a parallel region declared with OpenACC parallel. The compiler will understand from this directive that the next loop is safe to parallelize, right? Because this is implied by parallel. And the compiler will also know that it's not safe to parallelize this loop, because this is what we are telling it with this directive. So I move to the next example. Guess what we are doing here? A reduction, the same that you probably saw in OpenMP. So I just want to show you okay, this I may be a little quicker than this. Clearly this is wrong, right? It's wrong in so many ways, right? There is no reduction, there is a data race, so since it's quite late, I want to make it quick enough. So this will give you illegal address during kernel execution, of course. You cannot do this as well, because you cannot pass a pointer to the reduction. Okay, so you can only reduce on a number of types that are integers, double, float, and you can check the full list in this specification. But so this is what the final code looks like. You have to move the results to a scalar. You put it in reduction plus, and this is the same syntax that you saw for OpenMP, right? So it's pretty simple. And the compiler will take care of doing all the stuff that we've seen this morning. You remember thread synchronization, atomic operation. So the code is much simpler in this case, right? But concerning the example that we saw this morning, it's much easier to write, it's much faster to write probably, but you will still have to provide the GPU with enough parallelism. So if you now will try to do the porting of this CPU application that we've seen all the day long with OpenACC, it will be much faster, much easier, but you will still have to provide enough parallelism to the GPU to exploit the many threads, many cores that it has. Okay, so, and I want to close the lectures of today by somehow closing the circles. How do you do a dot product on the GPU? You don't write it yourself, you use a library, because CUDA made it, and it's certainly the best way to do so. And no, sorry, NVIDIA made it, and you probably cannot do much better than NVIDIA. And so there is one last directive that I'm introducing today, and this is open or pragma ACC host data use device. What does this mean? It's used to call libraries, and it's telling the compiler that the data that you have on the host for x and y, which are pointers, should be mapped to the pointers on the device. And this way you can access CUDA libraries and use CUDA libraries to do the computation with the variables that you have allocated on the host with a standard approach of CUDA malloc, that you have created with a directive here. So we have allocated implicitly here, and then you eventually pass these allocated variables on the GPU with this directive to the library that performs the computation. Guess why I'm showing this one? Well, because if you want to do the exercise, you have to call CUDA random, probably. Okay, so you do find much more. I mean, there are really a lot of directives, and there are all the specification, all the details on how to make a variable private, shared, and so on. I believe that you can gain more from trying to reproduce the results that we have done on the exercise with CUDA with OpenACC, and at the same time you can visit this web page where you do find all the details on the directives, and it's much better than a long boring description of all of them. And so this is an overview of how you can do the same accelerated computation with a more concise language, and I think you still have some time to try it and check out how it performs. In my case, the compiler outperformed me, so it makes better code than the one that I wrote. But well, try and check. Questions? What are the cons?
Compared to CUDA.
So I can tell you, well, this is it becomes a little bit more of a personal view, and it really depends on the code that you are working with. So, in my opinion, one thing that is not so, it becomes a bit of hard to deal with, is the fact that you have a mapping between the CPU and the GPU data, and it's something that you don't control, or at least is not so. You do control it with the update, with the data directive, and so on. But you know, when the code becomes large, if you are doing something wrong with an array that is not allocated or doesn't have the right size, with explicit programming, it's easier to produce errors, and these errors are meaningful. With implicit programming like this, you have to be a bit more careful, because the table of the memories that are on the GPU and on the CPU is not in your hands. I don't know if you can follow me.
It's like using OpenMP on a NUMA, like versus using MPI come tema special.
Yes, in a sense, yes. Yes, I mean you're referring to the various directives that private, shared, and stuff like that. Yes, with the additional, but this is true also for CUDA actually. The additional fact that you have also to take into account the synchronization between all this stuff. But I really want to stress that it depends a lot on what you are doing and and how much the memory and the structures of the memory becomes complicated. There are other things that you can do much easier with CUDA, like for example deep copies are much easier with CUDA. With OpenACC you have to be careful when you copy deep structures, and you should always have all the pointers copied in the right order.
There are no fundamental limitations in this approach.
I believe that one of the statements of PGI is that they try to have a performance that is in the order of 30% less. So if they are happy if with the directives you get 30% less performance than with a extremely well engineered explicit CUDA kernel. Honestly, I don't write enough OpenACC to tell you much more than this. It's widely used, so NVIDIA is really spending a lot of effort in developing this, and it's used by many projects, and so there are a lot of groups that are taking advantage of this approach.
But does it run only on CUDA devices? Or?
No, that's the other interesting part, and that's a pro. You saw TA, target architecture. This is meant to provide acceleration on any kind of device, also on other type of accelerators, but you may also produce OpenMP code with these directives. So you may generate a code that works both on the GPU and on the CPU, where the parallel region are translated into OpenMP code. And well, of course, we saw this morning that there is quite a difference between the structure of the GPU and the speed of each core and the number of cores on the GPU and the speed of each core and the number of cores on the CPU. But still, as far as I can tell, PGI is showing pretty nice results. I mean, they are sponsoring it, so I do expect that they show nice results. But I have seen some good performance also for code ported to accelerators with the OpenACC, and then moved back to the CPU, where the parallel region are translated to OpenMP regions. At the same time, I want to tell you also that OpenMP is also moving towards the definition of directives to exploit accelerators. Actually, they are already in place, so you can already use OpenMP to accelerate your code on the GPUs. It's a slower process, so I think you still get the best results with OpenACC, but also OpenMP is taking care of providing directives to accelerate code on the GPUs. Yes?
I didn't get exactly how this new syntax divides the blocks and the threads, as we saw in the explicit.
Yes, the reason why you didn't get that is because first, I
I haven't told you that. So, and second, because you can do that. So you can specify.
I cannot.
No. In principle, you can do that. Of course, the idea is that this is a set of directives that is general. So it's not bound to a specific architecture. So you can specify, and you may also specify different options for different target architectures. So you may decide that when you are targeting a GPU, you want that number of. I kind of made a rough statement when I show the results of an Excel info, right? So you saw gang and vector. So there is a slang of OpenACC that is actually mapped to blocks and thread. Okay.
However, the point is with this syntax, the 2, 3 constructs we saw in the last slides, can I call up a synchronization?
No, but the point is that you should totally forget about that. So the idea is you have a loop. I give the compiler the information it needs to generate the accelerated code. And the information you need are the information on the dependencies that are there in the loop, right? Because in order to generate, to write down the code that you did this morning, what you had to understand is what can be mapped to threads, block, what are the dependencies, right? So the idea behind this approach is I give the compiler the information it needs to generate an accelerated loop, and it's up to its implementation, given the information that I provide, to get the best accelerated code for the target architecture. You can control it. There are, of course, somehow the idea is also to provide very performant code. So in principle, you can control that. But I mean, this is an advanced topic, let's say, and the idea, see, the basic idea is to let the compiler do the acceleration. Okay, so I think you still have half an hour, and I can stay here for at least 1 hour more. So feel free to finish the CUDA example. Feel free to, have a beer probably. No, it's 5. Maybe it's time for a tea, not for a beer. Or start with the OpenACC exercise. So the OpenACC exercise is more or less the same of the other exercises. Okay. So in the OpenACC exercise, I'm providing you with curand.c function that removes all the boilerplate code that you have to add to call the library from OpenACC. It's actually a small change, but I mean, it's something that is not so much interesting. So what you have here is that you need to change main.c to make it run on the GPU. And as I told you, you will need to provide the GPU with enough computation to obtain a speed up. So, well, I think that, yeah, like in 20 minutes, I can show the results for the CUDA version and for the OpenACC version if you want. And, well, feel free to work on what you prefer. Okay, so for the braves that remain till the very end, I show very quickly the solutions. So let's start with the one in CUDA. So actually there is a comment in the README that you can do this much better. I think I will upload a better solution that I did yesterday night. But okay, so uniform is quite simple. It looks like the head. You just can pass the scalar variables a and b, and then you pass a pointer where you just calculate the global index and you scale all the numbers like you did in the serial version. Is inside circles is slightly more complicated, but it uses the same logic of the dot function. So I'm using unsigned int because that's what you can use for this atomic HUD that you saw before. Then came out from the discussion here that you can also use long int, and well, you start putting x and y from global memory, and you have generated this with CUDA random, so you have generated quite some random numbers with CUDA random, and I have my shared memory array which can host as many elements as the dimension of the threads per block. I set all the elements to 0, so actually each thread sets the elements to 0. Then you count if the x and the y are inside a circle, and if this happens, you set it to 1 and you stop. You have to stop because circles may be overlapped. So if you don't stop, you're counting too much. Then you sync threads, as you have seen for the dot product. I'm speaking in English because maybe someone in the microphone. Okay. And yes. And eventually, thread 0 sums everything in this local variable sum, and then does an atomic add to increment the value of count, which is the last input here, and the last parameter here to this function call, not parameter, to this variable in this function call. And so this is what for what concerns the kernels, and this is instead the main, where well, these are the old versions, where instead, well, you have the initialization of the random numbers, then you allocate circles on the GPU and you copy it, and then you allocate a variable on the GPU to store the number of hits, and you set it to 0, and eventually it's time to allocate random x and random y, fill them with curand, and then we use the kernels that we already prepared to do the computation and store the incremented value in n hits device. Okay, so what we have to do next is, well, we'll do some error checking, and what we have to do next is move it back to the CPU. So notice that I will continue to update the variable on the GPU, while the variable on the CPU will not be incremented, but just updated when necessary, so when I have to print the output. this is copy paste from the previous version, and I just free the memory at the end of this loop because I increment the number of trials. I've changed it here, so I have to increment the number of trials, so I reallocate the these two variables again at the beginning of this loop. One thing that I didn't mention is this. This is not very nice to the user because if someone changes the code and does something wrong, this will just stop and not show any error. But this is, of course, very important because we want to be sure that we are summing always on all the random points that we generated. Okay, so this is what, for what concerns the solution with the CUDA version. You have it online, so you can check it later. Yes.
Then, what is it? There is a difference in performance between data, which is global, so it's common to all blocks, and data that is private to the threads.
A huge difference. Yes. If you allocate a local variable, so that's actually the reason of, well, I mean, I don't think this will change much here, but I am moving the data from the global memory to the local memory to make this computation faster. I mean, this is not very relevant here, but access to local memory is super fast, more or less as fast as access to shared memory.
So what happens if you, instead of doing a shared variable between the threads, you have a global key?
That will be much slower because access to global memory, I mean, these are of course advanced topics, so you want to deepen your knowledge on CUDA programming. I wanted to give you an idea of how this how CUDA solves the approaches parallel problems, right, with this concept of threads and blocks. But yes, global memory is slow, shared memory and local variables are fast. 2 cycles, order of 2 to 10 cycles of the clock of the core of the GPU, while access to global memory is orders of magnitude slower.
Both in reading and writing?
Yes. Then there are, this opens a wide.
But no, because I was thinking, because in this case you would be limited anyway by because you're still using global global variables for because you have to read the coordinates of a random number.
Yes,
You're reading, so you're still limited by that.
Yes.
So it wouldn't change actually.
Yes, that's what I said. I mean, it's not going to make a big difference. But instead of accessing it this time and this time and this time and this time, I'm doing it only 1 and 2. So I'm saving 2 accesses. Okay, it's not much. I mean,
And can you do a shared variable that is not temporary?
yes, you could also use shared memory and copy all the data in a shared variable that you access from all the threads. That's what you mean?
Because here you're reallocating each loop. You're reallocating the time.
This one?
Right? Yes.
Ah, this
Each
one.
time. The time, yes.
No,
Each
wait.
time it is reallocated.
Temp is allocated here, right?
Yes, but you're calling is inside circles several times, right?
Not that many times.
Each iteration of the loop.
Yes, but how many times? I mean,
Okay,
because the
a
real
lot of
the real work is done. I mean, in this part of the code, right? So
Yeah.
what you do is that you call is inside circles GPU, with an array of elements that is bigger and bigger and bigger, right? I don't know if it's bigger or it's fixed size. It makes much more sense to have it fixed size, because the problem with this approach is that sooner or later you end up the small GPU memory. So it makes more sense to keep a fixed buffer and keep using it. And you can reach pretty quickly much better accuracies than what you can reach with this approach, because you end the GPU memory. But apart from that, even in this case, you call it like, I don't know, 10 times, 20 times, or we are not understanding each other.
If it must be that you must give enough data to the GPU.
Yes, you must give enough data to the GPU. Yes, the point is exactly this one. You need to provide data, let me make it simpler, but to the thousands of cores that you have in the GPU.
So you must have much more data when you have the cores in the GPU?
You need to provide, yes, a massively parallel amount of data. You cannot, so that's more or less the point of today. My idea for today was just like making this point clear. You need to provide a massively parallel problem for.
So if you have like, I don't know, 1,000 points,
Yeah.
around 1,000 points, this will be done just like one step.
If you have 1,000 points, this yes,
Oh,
if
right.
number of threads is 124, yeah.
That's why I was thinking, okay, then the allocation is important, because that happens like at each step.
Yeah, but what happens is that when on the GPU, the scheduler decides that a streaming multiprocessor will take care, yeah, whatever, the GPU will take care of doing the computation, it will allocate this block, your unique block, in the case that you are telling me now, to a portion of the GPU, and there will be some space in the local cache, the shared memory, which is fast. So there will be some space reserved, and that will be provided to the threads, and that will be used. So the point in the problem in what you're saying is not that you have the allocation of the shared memory. The problem is that you are using just a single block. So you're not saturating really the GPU, because to saturate, this is something. Because to saturate the GPU, you need a decent number of threads, generally more than 32. This is a more or less. This is again, we're going towards the hardware, and I want to go that deep, but you need some threads to saturate the streaming multiprocessor. You have seen it this morning, like with all the cores. But at the same time, you want to saturate all the streaming multiprocessors. So you need some threads to saturate the single streaming multiprocessor, and many blocks to saturate all the streaming multiprocessors.
It's always better to use the maximum number of threads possible.
No, that depends. Really depends on the algorithm. There is a lower limit. Running with one threads is not a good idea, but the best number of threads depends on the algorithm that you're writing, and mainly depends on the access of memory that you have, memory access pattern that you have. Yeah. No, that's it. And so I go very quickly. Well, I don't know if it's worth it, but I can show very quickly also the solution with the OpenACC. Well, it looks really like dot product, of course. Yeah, no, Chineka is not collaborating. Waiting. Come on. Okay. Okay, so this is very simple to parallelize, and we have already. No, well, there is a mistake here. Actually, I think. I have to check info. No, but we only have one pointer, so it's fine. Okay, so R01 is the only pointer that we have, and it's already there. So we are allocated in the somewhere below. We will see that, and this is how the reduction looks on the in the version with OpenACC. So you see it's much more concise. You just need to move the data to a type that OpenACC understands and move it back. And well, last thing is data allocation. So I use enter data to keep circles on the GPU, and then each time I create random, I pass it to uniform on device. Then I call these functions that you, if you remember, they had present, so they know that random x and random y are on the GPU already. And that's it. There is an implicit barrier at the end of this parallel region. So to try is a scalar and is updated. And this will update and tries and will print the result. I mean, it's quite late, so I'm sorry if I didn't go through all the details. We can discuss it maybe, if you want, in the next few minutes. I think I can switch off.